what I needed. Like I didn't have, I could have had a little bit more control because I didn't have as much other stuff that I had to be aware of all the time. I just turn my email off and turn off the attendance stuff and just worry about it later. But like when it's actually at school, we care a lot more about being in class, or like students are actually in class when they're in class. At some point at home, like I would just had you guys type here and by in the attendance or in the chat window, and I just used that to do attendance after class. So I didn't even worry about it while class is going on. I just worried about it afterwards. So like I didn't have to have the attendance window open and the Zoom window open at the same time and try to sort through it. I just was like, you know what, like we'll just do it that way. And it was able to like reduce some of the windows that I needed to look at or how much stuff I had to have open. And then like some of the, I think some of the schools, like the software they have run in the background that limits your access to stuff. I think that sometimes gets in the way and slows everything down and makes it a problem. So we, I'm still muted apparently. There. Okay. That's better. All right. Anyways, I think we're back here and things seem to be moving marginally faster. It didn't save that in there though for me. That's a bugger. All right, so let's type this thing in again. Woody, I am sorry that it's taking so long on this question you had, or that I haven't forgotten about it anyways. I'm just trying to get things to work here. All right, so there's that. We'll reset the window between -30 and +30 because those are the two biggest things on my list. What? I window, and then when I was done resetting my window, I just press graph. Yep. So I'm using just mostly the gray buttons that are at the top when I'm doing all my graphing stuff. Obviously, buttons to type stuff in, but these that I care about. Okay. So it looks like most of my stuff is happening pretty close to the y-axis here, right around the origin. So I'm going to go ahead and reset my window when my calculator's done thinking to like, I don't know, -5 and +5, probably more than I need, but I just want to be able to see what's going on there. So I can actually see the intercepts if there are any. So there's 2 there. And there's another one there and another one there. So it looks like I have something a little bit before and then right at -2. So like at 0.1, then -2. And then that looks like +2.1 right over, and then So this is interesting because the -2.1 and the +2.1 are definitely not on my RRT list, right? That tells me that those values are irrational. They are not something I should use for my synthetic division. In fact, if I try to use the synthetic division on them, it's not. I would need to know exactly what that radical is, but there's no way I can get a decimal and have it be like a fraction that I could use and have it not be a number that's on my list. So those have to be bad dudes. Good Lord. Oh, that's not what I want to press. Press that. Okay. So let's start doing our synthetic division. 2 or 3, because I know I can't use an irrational one. So I'm just picked -2 because it was the first one on my list. Would have been nothing wrong with oops. Check that real quick. Okay. So that's 10. 15. That's -30. That's give me 0. At this point, I could stop and try synthetically dividing the 4-term polynomial that I have left. But I also have another number to do that, because if I can get to a shortcut factoring thing from chapter 4, I'd rather do that than have to do the longer factor by grouping. Yeah. So there's that. That worked again. So I have the x plus 2, because that -2 synthetic division worked. It gave me the remainder 0. I have the x minus 3, because the 3 for synthetic division worked. It gave me the remainder 0, which is constant x coefficient, x squared coefficient. So x squared minus 5. X squared minus 5, does that factor? No, right? You'd have to use a difference of 2 squares to factor it, but 5 isn't a perfect square. So this is as good as we could do. Oops. If I did the square root of 5, that's going to give me right about that 2.1 number that I was looking at on the graph. So that was the actual value of that x-intercept that I estimated at 2.1 or -2.3, which is -2.3606, yada, yada, yada. And I'd have to have exactly the square root of 5 to do the synthetic division and have it work. And there's no way for me to look at the picture and get exactly the square root of 5 out of it. So we just have to avoid those ones. Does that make sense there, Woody? Okay. Cool. All right. So let's kind of finish up this method here. It's called the bend. And it says that if, or I'm sorry, we should say let f of x be a polynomial. We say if okay. Yes. All right. The question becomes, what do I mean by a bend? I'll come second. So the next part says the same thing, but instead of odd, we say even, we say 2. And then the last part says the same thing, but it says straight. And then we say, we say just exactly once. Yes, Megan. A-N. You're welcome. So what do we mean by bend, bounce, and straight? Let's draw some pictures here to kind of describe. So we're just talking about what the x-intercept looks like. So the bend, the graph is like curving one way, hits the x-axis, and then starts bending the other way. So it's kind of like, it looks like that. A bounce is the graph comes down, hits the x-axis, and then goes back up, or it could happen from underneath, right? Could go up to the x-axis, hit it, and then go back down. And then a straight is it just kind of goes straight through. So we can use this theorem to predict how many times we might have to use a number for the synthetic division, right? This one would have been quite helpful when we did number 6 in the homework, right, Megan? Because here we would have been able to look at the picture and go, oh, I see why there's so few solutions, because I'm going to need to use some of these more than once. Okay. So the next theorem we're going to have is called the Irrational Conjugates theorem. And it says for a polynomial f of x with rational coefficients we should have probably said equation, polynomial equation, f of x equals 0. We say that a plus b square root c is a solution to f of x equals 0. A minus b square root c is also a solution. So what this is saying here is simply that any of these irrational solutions or irrational factors are coming in pairs. You can't get just one of them, right? In that example that that Woody had asked about, we saw that we had square root of 5 and negative square root of 5 were our two irrational roots that we saw there. For the two irrational x-intercepts, like that negative 2.2 and positive 2.2. That's the idea, is that they have to be coming in pairs. You can't just get a single one. And the last theorem that we're going to add today is called the complex conjugates theorem. And this says something similar. So it says for a polynomial, f of x equals with real coefficients, a solution, a minus bi is also a solution. And what this is saying then is that if you're getting an imaginary answer or an imaginary solution or imaginary root, that these also have to come in pairs. You can't just get a single imaginary answer. You have to get them in pairs. Which again, we saw when we solved quadratics first semester, right? There's never a situation where you solve the quadratic where you got just one imaginary answer. You always got them two, right? You couldn't get one real answer and one imaginary answer. You always had to get either, two reals, one real, which was really the multiplicity, or two imaginary, right? So the same idea here. So we're just going to kind of formalize that a little bit. Just make up one. All right. So let's say we wanted to factor this following polynomial. Now it's going to be a doozy because I'm going to give you something with stuff going on so you can kind of illustrate what we're seeing here. Let's say we have this bad mama jamma here. Now, at first glance, you're like, yo, that's impossible. That thing is monstrous. And it's big, but it's going to be okay. We can handle this. So we know right away by looking at things, we can have 9 solutions or at most 9 factors. And those 9 factors, the rational ones are going to be the factors of 8 divided by the factors of 1, so just the factors of 8, really. And then we're going to go look at our graph and take a look at what's going on here. So let's go type this into our calculator. What's up, pal?
Oh, I'm good.
Oh, okay. I thought I heard an like you were getting ready to ask something and then you decided not to. That's okay. No big deal. So I'm just going to go ahead and type this into my calculator and look at the picture. So the steps really haven't changed much so far, right? I haven't done anything new. The new stuff is going to come when I start interpreting this picture that I get from looking at the graph and deciding what that means. Dang it, all. I have to say, at some point along the way, TI decided in its operating system that when you use the exponent button and then type something, it doesn't return you back to the main line. It keeps you in the exponent, which I just find so aggravating. It's like, just let me, if I need more than one thing up there, I'll just use a parenthesis. And if you want to make it like, shoot it all up there after I press enter and leave the parenthesis to show me that it's like, yeah, it's all up there, that's fine. But like, it drives me nuts trying to type in these polynomials. I screw it up half the time. Anyways, so I got it all typed in there, I think, correctly. Now we'll graph it from -8 to +8. And let's take a look at our picture, because here's where we can start using some of this new stuff that we found. And now I'm getting suspicious is that nothing's showing up, that maybe I typed something in wrong still. But we'll have to see. You see the bars on the side of the calculator moving up here? That tells you the calculator's thinking, or in this case, it looks like it's frozen, because that's how my computer's functioning right now today. And it's been just like a pretty clunky, disorganized, start and starty lecture because of it, and it's really making me feel bad that I'm doing a bad job at my job. Oh, good, it did do something. Great. Okay. So -1, we can see there's a solution there. And at +2. Everybody agree with that?
Yeah.
-1, is that a bend, bounce, or straight? So here at -1, that's the bounce, right? Because it's hitting it and then going back the direction it came. So that's the bounce. Now, one of the hardest things is going to be telling them the straights and the bends. So at +2, is that a bend or a straight?
Bend. There's like a little bend right below.
Yeah, it's hard to tell whether it's a bend or a straight, right? Like, let's zoom in a little bit closer. But it certainly, maybe it appears to be a bend, but 1 pixel of bend isn't enough for me. I want to take a closer look at that and see if I really take a sharp look at that, if I can tell what's going on. So I'm going to go from like +1 to +3. And take a look just in that section to see if I can tell what's going on. Where I give it a little bit more and now that's a much better picture, right? Do you guys agree? What do you think it is? That's a bend. Everybody agree? So again, like, you got to be careful. The straights and bends can be deceptive, especially when stuff is zoomed out and you have a big polynomial, like when the exponent is really big. It tends to be very steep, and your calculator has only so many pixels. It can't do a very good job of representing that. So you might have to do an occasional zoom in, especially if you're like, it feels like this should be used more than once. Maybe I screwed up, that straight was actually a bend or something. Like, be wary of that. Okay. Obviously, both of these are rational because they're on our list. So let's figure out the number of times we might use these things. So I'm going to make a little table with the number of times these solutions can be used. So each row of this table is going to correspond to like a different possible solution set. So I know that there's 9 total solutions that I could use, right? Since -1 is a bounce, the least amount of times that's going to be used is 2, right? Has to be an even number, at least 2. The bends had the least number of times it could be used is 3. We couldn't see any irrational solutions because there were no x-intercepts that were decimals, right? They're all whole numbers. So right now I have 5. So it could be that I possibly have 4 imaginary solutions, right? But this one could be used 4 times. That one's still 3 times. That would give me 2 imaginaries then to fill in the space. Or this could be used 3 times. That gives me no imaginaries. 3 times. That gives me 2 imaginaries. 3 times. That gives me 3 imaginaries. 3 times. That gives me 2 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 imaginaries. 3 ti Or instead of -1, we could be changing +2. So +2 could also have been used 5 times. Room for 2 imaginaries and 9 total. Or it could be used 7 times, leaving no imaginaries for 9 total. Now, I don't know which one of these 3 solution sets we're going to see. What I always do is I start with this one, the minimum number of times things get used, and then we'll proceed from there. And maybe I'll get to a point where it's like, oh, I think I can do this more. Or maybe I stop and I have something good I can do, I can use anyways. You know what I mean? Maybe you don't. It's okay. Is everybody okay with how I filled out this table? And kind of see what they mean? Megan? Okay. So I know that there has to be 9 total things in the row. So the minimum number of times a bounce can be used is 2. It could be used an even number of times, 2, 4, 6, etc. A bend, the minimum number of times it can be used is 3, but it's an odd, so it could be 3, 5, 7, etc. Okay with that? That's just from the bend, bounce, straight theorem is all that I'm using there. So now I'm going to fill them in. So like, okay, if the bounce got used twice and the bend got used 3 times, that's only 5 things, so the other 4 would have to be imaginary to get to 9. But it doesn't have to be just 2 and 3. This one could be 4 and 3. If I have 4 and 3, that leaves 2 more to get to 9. And it doesn't have to be that. It could be like 6 and 3. So 6 and 3 gives me 9 already. You kind of see what I'm doing now, Megan, in terms of filling the table out?
Yeah, just why did you put 3 or 2 trees? Or 5 or
Those are just the possible combinations of how I can do things. So like 2 could pair with each of those, right? 2 paired with 3, 2 paired with, each one of these could pair with 3, 2 paired with 3, 4 paired with 3, 6 paired with 3. But it can't be more than 6 because the next one would be 8, and 8 and 3 is too many, right? That's 11 total. We only have 9. So then I took 4. Well, 4 could pair with 2 and 4 could pair with 5, but it can't pair with 7 because that's too many. And like kept going. Or 4 can't pair with 5, or 4 can pair with 5. We didn't do that one. Sorry. Do you kind of see what I'm doing now in terms of just filling the table in? So this one had a lot of possibilities. Typically, you're not going to get something that has you're probably going to get something that has 2 or maybe 3 possibilities in terms of the rows. I picked a really complicated example because this was going to be the only example we had time for, so I want to make sure kind of a lot of things happened. So it wasn't trivial and you could use it. Yes? So it's this one because when we looked at the graph, all the things we saw were rational. So that's why that middle column was the irrational stuff was zeros. Because we didn't see any irrational things, so it had to be 0. Is that okay? Okay. Okay. So let's start doing our synthetic division. So I'm just going to pick one of these to start with. It doesn't matter which one. So I'm going to start with the -1. All right. And let's rock and roll. So we'll do our synthetic divisions. Okay, and I know -1 can be used at least twice, so I'm going to just use it again here without even stopping to think about it. So that worked twice. And I'm going to switch to the +2 because I know that can be used at least 3 times. I don't have to stop and I can just keep doing my synthetic divisions. And at this point, who's really glad that we don't have to do long division?
I'm pretty glad.
Yeah, right? Long division would just be like a booger right now, huh? So there's that. And I know this is going to work 3 times, so I'm just going to do it again. So one more time, and then we'll stop and pause and reassess here. So that worked again. I still have a 5-term polynomial though, so that's something that I probably don't want to try to handle with my factoring tree, right? So what are we going to do? Just going to try one of them again, right? If the -1 works, then I know it's going to work a second time, so I'll do it again. If the -1 doesn't work, I'll try the 2. If that works, I know it's going to work 2 times. And if neither of them work, I know I'm done because that thing then has to be all imaginary pieces. Is that okay? So it doesn't matter which one you try. You could try the 2 here. You could try the -1. Either it'll work or it won't. Do you know what I mean by work? What does not working look like?
Then not a 0.
Not a 0 at the end. Very good. That's exactly right. And notice that because the -1 worked once, I went ahead and did it again because I know it's going to work a second time. Because the -1 has to be used, you know, because it's a bounce, had to be used an even number of times. So another, you know, get to use it another time. Even though if you looked at that line there, you'd say, oh, that's something I could factor by grouping. If you wanted to stop there and do that, that would be okay, but I think the synthetic division is faster than the factor by grouping. All right, so let's take a look at what we got. So I have 1, 2, 3, 4 times that I got to use the x plus 1 factor. And then 1, 2, 3 times I got to use the x minus 2 factor. And then my leftover x squared plus 1 is not factorable anymore. So this is be my final result. And that was quite difficult, right? I don't think I asked you to do anything that long on the next homework assignment, but let me double check. So I guess I do have one of them that's an x to the 8th, but that's still shorter than the one that I had there. So I have on your next homework just 3 of these that I ask you to factor in part 1. And then in part 2, once you have it factored, you're just going to solve, which is easy, right? You just set each piece equal to 0 and solve them. You guys remember doing that from before? I'm just trying to circle back to that skill. That's not a new skill. That's something we've done before, right? Okay. So again, the first 3 questions will take a little bit of time, right? The second 3 questions should be pretty quick if you have the answers to the first 3. Because they're the same problem. You notice that, right? Or the same polynomial. So you're just going to use your answer from part 1 to do part 2. Which is nice, right? It's not like a whole nother factoring problem to do. Megan?
So how did you decide to stop?
Stop when I did? Because I had something that was quadratic there. I had a 3-term polynomial, which I know I can factor easily by hand if I have to. But x squared plus 1 isn't factorable, so I just knew I was done. You could have tried to do another division with -1 or +2. Neither one would work, at which point you would know that was your last step. So again, it wouldn't be wrong to do that. Usually, though, when I see 3 terms, I'm stopping no matter what. Because if it's factorable, it should be an easy thing to factor. Or at least a relative, it's a chapter 4 factoring problem. You know what I mean? So it shouldn't be bad in that regard. Okay. So next time we'll go through the homework, right? And we're going to take a day in class to work on some of these problems. So we'll just slow down for a minute. We'll do some in-class exercises. We won't go any farther forward with content. We'll just kind of work on this process where you can sit and work with a partner and work through things and practice using your calculator and feel like you really kind of get some more familiarity and a little bit more support than maybe you do trying to do this stuff at home. Sound fair? Okay. Again, I apologize for not getting a chance to do a little bit more of that to this point, but I wanted to get to here where we have all the tools together in one place. To really let you practice things. Okay? Okay. Well, thank you guys. Those of you learning from home, you guys can check out and head out. We're done for today.